In this presentation, we will be focusing on computed and direct radiography. So as an introduction to CR and DR, they're both digital types of systems. Digital imaging was originally developed in the 1980s and gained acknowledgement in the early 1990s, but was rarely actually used even with the development of PACS, which is an acronym for a Picture Archiving and Communication System. PACS is used to store both 3D and 2D radiographic images and other imaging files such as CT scans and MRI. Computed radiography to begin, it was the first modernized system to replace film screen radiography, which utilized multiple screens, cassettes, and developed the final image with chemical solutions or physical dark rooms. CR was just beginning to develop to replace CR was beginning to develop to replace the screen film method, and it used a PSP plate, and it was read with a laser scanner device. In this period, other digital technologies were surfacing, such as FOV, which is a large field of view, X-ray phosphors, and optical lens to focus the X-ray, to a narrowed CCD, which is another acronym for Charged Coupled Device Photodetector Panel. To clear up any confusion, a CCD is basically a light-sensitive circuit that stores data from the light in the form of pixels, which is then converted to an electric charge. CR is critiqued for having mechanical parts that wear down over time. DR doesn't have this, and CR doesn't save nearly as much time over traditional radiography as to the extent that DR goes. So to introduce DR, moving on, it has many integrated features and even wireless functions to transmit data to the receiving computer. There is a great lack of mechanical parts, which is good. It causes a longer life of the machines due to an integrated system called a TFT that houses closer components, and it allows higher travel speeds for the digital information to move across. The final image in DR can be compensated in post-processing if the exposure brightness is too high, and then it can be formatted, sent out to the radiologists and anyone else more readily. Post-processing is basically just after the original radiograph is taken, it can be edited a little bit instead of having to retake it. DR is expensive, but large-scale facilities and hospitals are utilizing them more often. The purpose is to serve the most amount of patients in the least amount of time. It's a cost-effective type of reasoning. The benefits and disadvantages of computed radiography and direct radiography are debated due to the different costs and the necessity of certain features. These will be discussed moving forward. So what's the big deal with CR and DR? Basically, I was determined to select the topic because they're both popular modalities that can be really considered the heart of a radiologic technologist's career, which many students, like myself in this program, are studying to become. As I mentioned, when a facility chooses to use one system over the other, it affects mostly all professionals involved in a patient's recovery, even all the way to the receptionist who schedules the patient's appointments. The use of DR at a busy location, more patients can be scheduled in an hour's time than with CR. It's just more cost effective that way. Imaging speeds will be discussed in detail later, and the nurses will have more individualized time to tend to the patients and communicate personally with them, rather than rushing because of the time budget while using CR. Even a less efficient rad tech has more room in the aspect of time to position a patient as if that same RT were using a CR system. So, like I had mentioned, they're both types of digital radiography. They both are successors to screen film. Now, computed uses cassettes that must be read one plate at a time, and they take about 25 to 90 seconds each. Cassettes contain a PSP, which includes main layers of the main protective layer, a phosphor or turbid layer, reflective, conductive, and support layers. CR plates do have a limited lifespan because they are physical hardware. They will wear out over time, and you'll have to discard them. There's a few steps in how to create a radiograph with CR. It's basically, You place the imaging plate in the Bucky tray first before the exposure is made, and then the imaging plate will be taken out. The latent image will be embedded on there. Latent image is what you can't see, it's just in there digitally. And then it's placed in the image reader where lasers decode the light information, loaded onto a computer. So light to digital pixels is not completely digital, it's kind of analog, that's why it's not quite as true to the digital radiography name as DR is. And then here on this slide you can see the PSP image acquisition. There's different steps on it. Inside the cassette is the PSP, which stands for photostimulable phosphor plate. That consists of the layers from top to bottom, as I had mentioned earlier. The phosphor layer is the one that distributes the phosphor crystals randomly in the active layer. The X-rays ionize the phosphor atoms. They trap about 50% of the electrons in the conduction band. That forms a latent image. And then the electrons trapped are read by the cassette reader. So if the same image receptor is used, this process must be repeated for each different position, including the time to erase the image stored on the plate. This can be kind of a lengthier process when the patient may be in pain or waiting for you for the next action. Erasing the data itself takes about 45 seconds in addition to the 2590 it originally takes to read the plate. Or, display the image. And it's less efficient and irresponsible for an RT to not erase the cassette after each use. Put them to the side because if mistakenly seen as a fresh cassette, a new image cannot be stored on that occupied cassette, which is some more wasted exposure on the patient and it uses up time. And that also violates ALARA, which states that the patients must receive the lowest radiation dose achievable. It can even be said by some people that the CR may contribute to the chance of overexposure because of outdated mechanics that allow for this to happen by inexperienced technologists. But there are still many relevant reasons as to why CR is still preferred in many facilities. So direct radiography. There's no cassette in this. It's all hardware, close tucked wires. There's no removable imaging hardware that can be physically read. It's got built-in digital imaging sensors into the table itself, into the wall-mounted image receptor, or connected to the computer by a cable. As mentioned earlier, DR uses a CCD and a TFT through indirect and direct capture methods. It also creates a great histogram that's unmatched by CR. So indirect and direct capture, there are two subtypes. CCD, which is the charge-coupled device, and the thin-film transistors. Basically, as you can see here in this image, the X-ray it reaches the built-in image receptor and it directly converts it into a pixel, which is little forms that can be read by the computer rather than physical light being decoded by a physical laser. It's a very digital process. The CCDs, to understand how that works, it consists of single tiles that are joined by tiling, and the seams between them may create unequal response or blurriness, which is actually a disadvantage to CCD direct radiography. In TFT, the X-rays are absorbed by the photodetectors and converted to transmittable electrical charges, like I was explaining. The indirect capture causes resolution loss sometimes because of the scintillators. Direct capture only uses a photoconductor and has more uniform detection ability over indirect. So with a facility that's choosing DR, direct capture is the way to go. The most advanced DR detectors have automatic beam detection, which capture more latent data and have even more dose efficiency accuracy over CR. So as for CR is still praised because of its retrofitting ability, how it's able to install onto existing hardware, existing devices, and upgrade it to a newer CR system, whereas DR cannot be retrofitted oftentimes, and completely new hardware may have to be installed. And along with the new retrofitting function that DR is going to have, that is called automatic beam detection software, it contains certain elements such as gadolinium oxysulfide and cesium iodide. That helps with that. Now, moving on to this slide here, there was an article that I was reading from Radiology Today. It was about a facility in Louisiana called Our Lady of Lourdes Regional Medical Center. It was a 200-bed facility that was in the process of converting the entire facility to DR at the time. The director of radiology in that facility has been in contact with General Electric Healthcare for the conversion for about 4 years because they didn't quite have that exact setup available yet that they wanted. That's one downside, aside from the high cost of DR, is that since it's such a new technology, the softwares and the specific setups may not be available yet that all facilities want. But after the facility in Louisiana finally went completely digital, the patients, the rad techs, the radiologists all benefited from decreased turnaround rate of the patient coming and leaving the facility. The radiology detector also determined that DR returned significantly faster results, less than a minute. Compared to CR, the productivity of the facility, it increased by 12 to 15%, which is quite a lot when you think of how many patients they see on a daily basis. Even with the cost of DR factored in, it seems like the time was right for the Our Lady of Lourdes facility to upgrade. So it seems that basically, as it was stated in the article, DR is superior to CR in almost every aspect, but many facilities will continue to offer a blend of both because it's just too expensive at times. So some key takeaways of CR and DR. Let's see here. I have a better understanding now of how the receptors are established and the responsibilities within the two digital systems, what makes them better or worse than the other component. As it's apparent, DR has the clear advantage compared to the predecessor CR, but CR is still a great choice. It is a lot slower, but the same accuracy of an image can be reached with little to no resolution difference. It is a little outdated compared to direct, but it is still very applicable, very usable in the modern day. And there you go, see some advantages there of CR, their ability to produce consistent high quality images, low cost of storage, expansion. It's a well-developed system that has been around for quite a few years now, and it works well. That's why a lot of facilities just choose not to upgrade to digital. There are some disadvantages, like I mentioned, is dose creep, where eventually the exposure of radiation to the patients may increase over time because there's no automatic control that resets the radiation exposure amount of kVp and mass as DR would. So disadvantages of DR is that it's a new technology. It's significantly more expensive than CR. CCD isn't quite worked out as well yet as the TFT direct option of direct radiography. CR is still the most convenient choice over DR for mobile radiography. That's the one that's been tried and true. It's tested to be the best at the moment. And image quality isn't quite as much higher as how much more it costs than CR. And then there's no cassette, removable hardware, and post-processing is so much faster than CR. Exposures can be compensated for. Patients don't have to be left while you go and read your latent image on the cassette. DR take care of that for you, and you can view the image also instantly. And the images can be transferred to the associate doctors much faster. That's all for this presentation today. I hope you learned something new.